When Apollo astronauts returned from visiting the moon, they brought some of it back to Earth. And when scientists analyzed those lunar samples, they were surprised by what they found. Because although these rocks came from another world, in a way, they were strangely similar to rocks from Earth. And this wasn't the first time we recognized that some aspects of our moon make it a bit of an oddball. In fact, us having a moon at all is unusual. Almost all of the moons in our solar system orbit planets beyond the asteroid belt, like Jupiter and Saturn. And our moon is also big, both absolutely and compared to Earth. It's almost the same size as Mercury and more similar in size to its parent planet than any other moon in our solar system. So where did our unique moon come from? It turns out those lunar rocks are a clue, pointing to the origin of our closest cosmic companion, an origin even stranger than you might imagine. Because the moon's formation might have something to do with that time the Earth ate a planet.
We recently partnered with toy designer David Silva to create a scientifically accurate, hand-painted figure of a woolly mammoth. The 1/18th scale mammoth figure is designed based on the latest science and painted using references to modern-day creatures living in the same environments. The mammoth is available now through BackerKit. More information is in the description.
In the beginning, more than 4.5 billion years ago, our solar system was a busy place. At its center, the newly formed sun was surrounded by a cloud of gas, dust, and debris. And in this protoplanetary disk, small rocky particles were being pulled together by gravity, smashing into each other and combining to form bigger chunks of material. These violent collisions continued until eventually entire planets took shape, including Earth. But this early version of Earth was missing something very familiar: its moon. Scientists think that the Earth was probably flying solo for somewhere between the first 60 to 250 million years after the formation of the solar system. And over the years, there have been lots of ideas about the moon's origins. Scientists once thought it might have formed at the same time as Earth, in that protoplanetary disk. Or maybe Earth just captured it from somewhere else in the solar system, like from one of our closest neighbors, Venus. But none of those ideas explain all of our moon's quirks and those Apollo collected rocks. So what did scientists find in those lunar samples exactly? Well, when they analyzed the samples, they found that the amounts of the stable oxygen isotopes, oxygen-16, oxygen-17, and oxygen-18, match very closely with what's found in rocks from Earth. And this similarity hinted at where the moon came from. See, isotopes are versions of an element that have the same number of protons but different numbers of neutrons. This gives them the same chemical properties but slightly different masses. Now, isotopes that are radioactive are unstable and break down over time, but stable isotopes can remain the same practically forever. So, when it comes to rocks from beyond Earth, the ratios of stable isotopes in a sample are like unique fingerprints for how and where in the solar system that rock formed. And scientists found that it wasn't just oxygen isotopes that the moon and Earth had in common. Other stable isotopes were a close match as well. They realized these similarities were too much to just be coincidence. The more likely explanation was that the moon had formed from part of the Earth itself. But even though Earth and moon rocks resemble each other in some ways, researchers noticed some differences too. Like, they discovered that lunar rocks were lower in volatiles, which are elements that vaporize easily with intense heat. And minerals in the Apollo rock samples hinted that the moon was once covered in a vast, deep magma ocean, which meant that it must have been very hot when it formed. Another core difference between our planet and the moon is that the moon has less iron overall than Earth. Its tiny iron core makes up only 1 to 2% of its total mass. That's pretty small compared to Earth's core, which accounts for a whopping 30% of its mass. So, with evidence piling up, scientists were beginning to form a clearer picture of where the moon came from. It seemed to have started out hot and formed from iron-poor material that likely came from Earth. But how? Was there a way to explain the moon's size, its isotopic similarities with Earth, its small iron core, its lack of volatiles, and its once deep magma ocean? The simple answer is yes. It started with a bang. See, in 2001, astrophysicists mathematically modeling possible moon-forming events landed on something interesting. Through a model now called the canonical impact, they could reach a reconstruction that fit many of the observations about the moon. In this model, the moon formed from a giant impact, one where a protoplanet the size of Mars crashed into the early Earth. The researchers estimated that the collision would have released a huge amount of energy, partially melting and vaporizing both planets. And the impact would have launched debris into space that eventually formed a disk around the Earth. Now, most of the debris in the disk was too close to the Earth to form big chunks without being disintegrated by the planet's gravity. But material further away could have escaped this destructive force, allowing it to collect together to form the moon. Once the dust settled, the Earth was slightly larger than it had been before, and it had a moon. Their simulations produced an Earth and a moon of the correct size and iron content. They also explain why the moon started out so hot, and importantly, how it could be partially made of material ejected from Earth. Scientists named this ancient protoplanet that collided with Earth Theia, after the Greek titan who was the mother of the personification of the moon. But there was still one problem. Canonical impact simulations predict the moon-forming disk would be mostly made of material from Theia, not Earth. And remember, lunar rocks have a stable isotope fingerprint similar to Earth's, too similar for them to be mostly made of Theia. It's possible that, by chance, Theia was Earth-like isotopically, but that seems unlikely because the stable isotope ratios of other inner solar system bodies, like asteroids and Mars, are not Earth-like. Researchers call this mismatch between the model and the observations the isotopic crisis. So, for years, they've been adjusting these models to potentially explain why there aren't clear isotopic traces of Theia in lunar rocks. Like, maybe the Earth was initially spinning faster, or maybe it was more molten when it was hit. They also tried changing the size of Theia and modeling many little impacts instead of one big one. Or it could be that Theia was moving so fast that the impact was a hit and run, where Theia smacked into Earth and then continued on its way. Another possibility is that the material from Theia and Earth somehow mixed together really thoroughly after they collided, creating the isotopic similarities. Some of these ideas are promising, but they either rely on scenarios that seem far-fetched, don't match all of our observations, or need more data to support them. For years, none seemed to provide the perfect solution. But a new impact model published in 2022 might solve the crisis. In this study, the researchers simulated moon-forming impacts at a higher resolution. Instead of only using 100,000 to 1 million simulation particles to model the impact like most studies, they tested different scenarios using up to 100 million particles, the highest resolution ever attempted. And in their simulations, the Earth is struck by Theia, and then a giant blob of material is immediately flung away from the impact. Shortly after, a smaller chunk of material slingshots off the far end of the blob to become the proto-moon, and what's left of the main blob swings back and re-impacts the Earth. The proto-moon then settles into a safe, stable orbit where it eventually becomes the full-fledged moon. And all of this takes place within a matter of 35 hours. Their simulations predicted that the outer part of the moon could be made of up to 60% material from the Earth, with more of Theia beneath the surface. This could solve the isotopic crisis by explaining where some traces of Theia are hiding. But where is the rest of it? How could an entire planet just disappear? Well, in 2023, scientists published another new paper suggesting the answer may be a lot closer to home than we thought. See, there are a couple of anomalies deep in Earth's mantle at the boundary between the mantle and core where shear waves produced by earthquakes slow down significantly. These mysterious areas are called Large Low Velocity Provinces, or LLVPs, and the changes in the shear wave speed tell scientists that these continent-sized LLVPs are made of something different than the surrounding mantle. We know this because seismic waves change speeds when they encounter materials of different densities. And because Theia was likely a fully formed protoplanet when it hit the Earth, with its own mantle and iron core, the scientists argue that these LLVPs are leftover chunks of Theia, still inside Earth. Remember, in models of the moon-forming impacts, some of Theia's mantle was flung into space to become part of the moon, but its core and the rest of the mantle would have been swallowed up by the Earth. In other words, Earth ate most of the planet. The researchers argued that Theia's mantle would have had more iron and been denser than Earth's, and it would have mixed into Earth's lower mantle during the moon-forming impact. Their models predict these denser, iron-rich Theia bits would sink downward through the mantle over time and collect together in two large areas at the edge of Earth's core, right where the LLVPs are found today. If the researchers are correct, that could mean there's direct evidence of Theia still inside Earth. But the authors admit they can't completely rule out that the LLVPs aren't something else entirely. So, in the end, what does all this tell us about how our moon came to be? Well, scientists agree that the best explanation for the origin of the moon seems to be a giant impact between Earth and Theia, but the exact details are far from settled. And hopefully, a combination of methods, from modeling to analysis of lunar rocks, can help unravel the moon's mysterious origins. But for now, we're still searching for the missing pieces of the puzzle, and for solid evidence of Theia hiding either under the lunar surface or somewhere beneath our feet. Hey, want to see the next episode of Eons early before it comes to YouTube? It's a good one. It's about how we may have the Himalayas to thank for giant flightless birds in Madagascar, the disappearance of plants from Antarctica, and the expansion of grasslands in North America. It's available right now for free on the PBS app or on pbs.org. The PBS app has a huge collection of documentaries from Nova, Frontline, and more, as well as shows from our PBS Digital Studios friends like Be Smart, Spacetime, Weathered, and Monstrum. For those in the US, you can download the PBS app on your smart TV or favorite mobile device. And everybody, including folks outside the US, can also watch it on pbs.org at the link below. So we're slowly figuring out what Earth looked like in the beginning, but what about the future? Find out in our episode, what will Earth be like 300 million years from now? And we're over the moon for this month's Eontologists. Addie, Annie and Eric Higgins, Carl Wofel, Jake Hart, John Davison Ing, Juan M., Melanie Lamb Carnevale, and Raphael Hasse. Become an Eonite at patreon.com/eons, and you can get fun perks like get access to behind-the-scenes content, including clips from Eon shoots. And as always, thanks for joining me in the Ken Barnes studio. Subscribe at youtube.com/eons for more primordial ordeals. Was there a way to explain the moon's size, its isotopic similarities with Earth, its small iron core, its lack of volatiles, and its once deep magma ocean? I'm Ron Burgundy.